Hey guys, this week I am actually recording this video in my office, sort of unscripted really quickly because I've been having some technical issues today with my computer. So hopefully I can get this done in a single take. So it's a little different than my normal videos. Welcome to another exciting video about rocks and fossils. My name is Benjamin Berger. I'm an associate professor of geology at Utah State University. And in this two-part video series, I'm going to summarize the 10 most common methods of finding the absolute age of rocks and fossils. So throughout a lot of my videos, I will toss out various ages for certain time periods. And so what I thought I'd do with this video is kind of informally talk about the ways in which geologists determine the absolute age of rocks and fossils, and the sort of the methods of going about obtaining those ages. Now this video is going to go into a little bit more depth than most introductory geology classes, but I wanted to make this video so that you would be familiar with the different ways scientists determine the absolute age of geological materials such as rocks and fossils. So this video is actually split into two parts, and this video being the first, I'm going to talk about the first 5 most common methods of dating geological materials. Now, the first thing to consider in dating rocks and fossils is what precisely you're actually dating. There are 4 basic moments that determine the start of the clock in measuring the age of geological materials. The first is a phase transition, such as the moment liquid lava or magma cools into a solid rock or crystal. The second is the death of a biological organism. The moment an organism, a plant or animal dies and stops taking in new carbon atoms from the atmosphere or from food sources. The third is the burial of an artifact or rock and how long it has remained in the ground. And the fourth is the exhumation of that artifact or rock, so how long it's been exposed to the sunlight. The second thing to consider is the range of time that the method can be used for. For example, you can't use a stopwatch to tell what year it is, whereas you can't use a calendar to measure a runner's time. So you need to be aware of the scale of time that you're trying to measure. Some methods are great for durations of time in the 1,000-year scale, while others are better at determining ages in the million-year scale, and others can be used at the billion-year scale. So if you're using a method designed for the million-year scale for something just a few thousand years old, it's going to yield erroneous results. Now, before I dive into all of these methods, I want to review some of the fundamental chemistry so that you can understand the processes involved. If you want to learn more, I highly recommend taking a geochemistry class like the ones we offer here at Utah State University or at a local university or college near you. Atoms are composed of 3 parts: protons, neutrons, and electrons. Protons have a positive charge and electrons have a negative charge, whereas neutrons are neutral. Both protons and neutrons each have an atomic mass of 1, while electrons have a teeny tiny amount of mass that we're going to just ignore. To determine the atomic mass, you can add the number of protons and number of neutrons together. So an atom with 6 protons and 7 neutrons will have an atomic mass of 13. Electrons travel around the protons and neutrons, which are held in the nucleus of the atom. Now, electrons are kind of flighty, and they occupy orbital shells around this nucleus. Electrons can easily be stripped off of the nucleus, and this process is called ionization, leaving the atom with a positive charge, or they can be added to an atom, giving the atom a negative charge. Electrons like to fill these orbitals in sets. So some atoms frequently lose or gain electrons, making them more or less reactive to other atoms. Now, electrons are really important because not only do their movement provide electricity, they also determine how atoms bond together to form molecules. The periodic table of elements is arranged by the electron orbitals of each element. If an atom contains a full set of electrons in the orbitals, the resulting atom is called a noble element, and it doesn't react to other atoms forming bonds. These noble elements are all gases at Earth's surface temperatures and pressures, and hence are called the noble gases, and they occupy the far right-hand column of the periodic table of elements. Element names, however, are not determined by the number of electrons, but by the number of protons, or atomic number. For example, carbon has 6 protons, while nitrogen has 7 protons, and uranium has 92. However, if the atom is neutrally charged, it will contain an equal number of positive protons and negative electrons. The number of protons in an atom is called the atomic number, which determines the name of the atom. For example, all atoms with 6 protons, no matter how many neutrons or electrons, will still be called carbon. Uranium, with 92, is the largest naturally occurring atom. However, chemists have produced synthetic atoms in labs with atomic numbers as high as 118. However, these are highly unstable and they quickly fall apart in milliseconds, so you will not find them in nature. Atoms can be unstable or they can be stable. Unstable atoms are radioactive and they produce energy as they decay or fall apart. The decay of each atom is purely random, making them an excellent source of randomization in computing. Some atoms can be made unstable when the number of neutrons differs too much from the number of protons. So, for example, all carbon atoms contain 6 protons, but they can have 6, 7, or 8 neutrons. An atom with 6 protons and 6 neutrons is called carbon-12, since it has an atomic mass of 12. An atom with 6 protons and 7 neutrons is called carbon-13, and an atom with 6 protons and 8 neutrons is carbon-14. These are called isotopes, from the Greek word iso, meaning same or equal. They are all carbon atoms, but differ only in their mass. They bond the same, they have the same chemistry to each other, but they differ only in the number of neutrons, and hence differ only in atomic mass. There could be carbon-6, 7, carbon-8, carbon-9, carbon-10, carbon-11, but these atoms differ too much from the number of protons and neutrons, and they're highly unstable and don't occur naturally. This is true if carbon atoms have a mass greater than 14, meaning they have like 15, a mass of 15, 16, 17. They could theoretically exist, but they're so unstable that they don't. They fall apart. When isotopes are unstable, they're called radioactive. So radioactive isotopes can have very short residence times, measured in milliseconds, hours, days, or years, while some have very long residence times, measured in millions or billions of years before they decay. Geological dating uses the longest of the unstable isotopes for dating. So, for example, carbon-14 has a very long residence time, while carbon-12 and carbon-13 are stable and they don't decay. All right, so now you know a little chemistry. Let's look at the 10 most common methods of finding the age of rocks and fossils. The first one is radiocarbon dating, or C14 dating. Now, as I mentioned before, carbon with 6 protons and 8 neutrons, or carbon-14, is radioactive. It decays. The decay of carbon-14 to nitrogen-14 involves the loss of a proton. So for example, carbon-14, half of the atoms will decay to nitrogen-14 in 5,730 years. That's called the half-life, which is when half of the atoms in a sample have decayed. Note that the decay is expressed as an exponential rather than linear function of time. This is similar to the rate of change as applied in business, like in finance, like determining computing compound interest rates for credit cards or for mortgages. So exponential decay is the same process. It's the same process you observe when you watch kernels of popcorn popping, that the rate of the new popped corn is dependent on the ever decreasing amount of kernels that are being heated. So radiocarbon dating was first developed in the 1940s. It was pioneered by Willard Libby, who had worked on the Manhattan Project in developing the atomic bomb during World War II. After the war, Libby worked at the University of Chicago on developing radiocarbon dating, for which he actually won the Nobel Prize in Chemistry in 1960. So the science of radiocarbon dating has been around for a long time. Now, radiocarbon dating measures the amount of time since the death of a biological organism, the moment an organism, a plant or animal, stops taking in new carbon atoms from the atmosphere or from food sources. It can be only used to date organic materials that contain carbon, such as wood, plants, unfossilized bones, charcoal from fire pits, and other material derived from organic material. Since the half-life of carbon-14 is 5,730 years, this method is really great for determining the age of material that's only a few hundred or a few thousand years old, with an upper limit of about 100,000 years. So radiocarbon dating is mostly used in archaeology, particularly in dating materials during the Holocene epoch, or the last 11,650 years. The first step is to collect a small piece of organic material to date. You want to be very, very careful not to contaminate the sample with organic material, such as the oils in your own hands. The sample is typically wrapped in aluminum foil to prevent contamination from carbon. In the early days of radiometric dating before the 1980s, labs would basically count the decay in the sample, measuring the radioactivity itself. So the more radioactive a sample was, the more radioactive it was, the more younger it would be. So more recently, since the 1980s, there's this new class of mass spectrometers that were developed, and this gives the ability to directly measure the atomic mass of atoms in these samples. However, the steps are a bit complex, but they yield a more precise estimate of age. The steps involve determining the amount of carbon-14, as well as the two stable types of carbon-13 and carbon-12, since the amount will depend on the amount of material. Scientists look at the ratio of carbon-14 to carbon-12 and carbon-13 to carbon-12. The higher the ratio of carbon-14 to carbon-12, the younger the material is, while the carbon-13 to carbon-12 ratio is used to make sure that there's not an excess of carbon-12 in the first measurement, and to provide a correction if there is. Now, one of the technical problems that need to be overcome was that traditional mass spectrometers measure only the atomic mass of atoms, and carbon-14 has the same atomic mass as nitrogen-14. Nitrogen-14 is very, 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 very common. It's a very common component of the atmosphere. It's in the air that surrounds us. And of course, this is going to be a problem. So in the 1980s, a new method was developed called the accelerated mass spectrometry method, which kind of deals with this problem. The first step in the process is to take your sample and combust the carbon in a stream of pure oxygen in a special furnace. Another method is to react the organic carbon with copper oxide. So both of these methods are going to produce carbon dioxide, which is a gas. Now, the gas of carbon dioxide, which is often cryogenically cleaned, so they freeze it down to a solid and then re-release it, is then reacted to hydrogen at 550 to 650 degrees Celsius, so very hot, in the presence of a cobalt catalyst. And what this does is it produces pure carbon in the form of powdered graphite of the sample and water. So this graphite then can be held in a vacuum, and you do that to prevent the contamination of the nitrogen-14 that's all in the air around us. The vacuumed graphite powder is then purged with ultra-pure argon gas to kind of flush it and remove any nitrogen-14 that would, if it's in there, would ruin the measurement. And usually this is done in a glass vial. Then this graphite, this pure carbon, is then ionized, adding electrons to the carbon and making it negatively charged. So then any lingering nitrogen-14 is not going to be negatively charged in the process because it has that additional positive charged proton. An accelerated mass spectrometer then spins the negatively charged atoms, passing them through the machine at very high speeds as a beam. Now this beam will have carbon-14, but it's also going to have ions of carbon-12 bonded to 2 hydrogen atoms, as well as carbon-13 bonded to 1 hydrogen atom. And all of those, of course, have an atomic mass of 14. Now, to get rid of that hydrogen, these carbon atoms are shot through a stripper that strips off or removes those hydrogens. And then they move, after that, through a second magnet, and the resulting atomic spread of the atomic mass of the carbon-12 and the carbon-13 and the carbon-14 are measured on a detector because you've changed the atomic mass. So you stripped off those hydrogens, so now they have different atomic mass than 14, so now you're going to get ones that are going to hit at different points because of differences in the atomic mass. So you'll get carbon-12, carbon-13, and carbon-14. So now you have what you need to do to determine the age. So the ratio of carbon-14 to carbon-12 is calculated, as well as the ratio of carbon-13 to carbon-12. And you basically compare this to lab standards. So the carbon-13 to carbon-12 ratio is used to correct the ratio of carbon-14 to carbon-12 in the lab and see if there's an excess of carbon-12 in the sample due to fractionation. Now, isotopic fractionation is a really fascinating, it's a huge topic in geochemistry because it has all sorts of interesting tools and implications that you can use for it, but I'm not going to go into it. But basically use that second ratio to correct the first ratio. Make sure you just don't have too much carbon-12 in the sample. And so you add a little correction. So to find the actual age in years, we need to find out then the initial amount of carbon-14 that existed at the moment that the organism died. Now, carbon-14 is made naturally in the atmosphere from nitrogen-14 in the air. In the stratosphere, these atoms of nitrogen-14 are being hit by cosmic rays from the sun, which bombards the nitrogen-14 with thermal neutrons. And this produces carbon-14 and an extra proton, or a hydrogen atom. This process is dependent on the magnetic field from the Earth and solar energy, which vary just slightly in each of the hemispheres. And they also vary when there's solar anomalies happening, such as solar flares. So using tree ring data of looking at carbon-14 to carbon-12 ratios, we actually know the year of each of those tree rings. So we can actually build a calibration of carbon-14 to carbon-12 in absolute years for the last about 10,000 years. And there's two ways that we can report the age of materials dated this way. One is to apply these corrections, which is called radiocarbon calendar age, or you can report the raw data determining solely from the ratio called carbon-14 dates. Radiocarbon calendar ages will be more precise than simple carbon-14 dates, especially for the older dates. So the older they are, they're going to, that calibration is going to have more of an effect. There's one fascinating thing about determining the initial carbon-14, carbon-12 ratios for materials during the last 100 years. Because of the detonation of atomic weapons in the 1940s and testing of atomic weapons in the 1950s and 60s, the amount of carbon-14 in the atmosphere increased dramatically after World War II. And you see this in the tree ring data. You also see this in direct measurements that have been made on the isotopes of carbon in the carbon dioxide of the atmosphere. Now, this fact was actually it was used by neurologists studying brain cells, and this led to the medical discovery that new brain cells are not formed after birth. As people born during the 1940s and 1950s, today, they still have higher levels of carbon-14 in their brain cells than if their brain cells formed much later in their lives when there was less carbon-14. So radiocarbon dating works really great, but it's kind of like a stopwatch. It's not going to tell you much about things older than 100,000 years. So for dinosaurs and for older fossils or rocks themselves, it's the next method that's more widely used. Potassium-argon dating. Potassium-argon dating, it's a great method for measuring ages of materials that are millions of years old. But it's not going to be very great to looking at something that's only a few thousand years old or something that's just a few hundred years old. Potassium-argon dating measures the time since a phase transition from a liquid to a solid took place, such as the moment liquid lava or magma cools into a solid rock or crystal. It also requires that the material contain potassium in a crystal lattice structure. Most common minerals sampled for this method are biotite, muscovite, and potassium feldspar, potassium feldspar groups such as orthoclase. These minerals are common in volcanic rocks and in ash layers, so making this method sort of ideal in measuring the time when volcanic eruptions occurred. Now, if a volcanic ash containing these materials are found deposited within or near the occurrence of fossils, a precise date can often be found for the fossils, or a range of dates, depending on how far stratigraphically that ash layer is found from the fossils. Potassium-40 is radioactive, but with a very long half-life of 1.26 billion years. So it makes it ideal in determining ages in most geological time ranges measured in millions of years. So carbon-40, it decays to argon-40, as well as calcium-40. Now, argon-40 is a gas, while calcium-40 is a solid, and it's very common in rocks. Hence, what we want to look at is the amount of argon-40 within a crystal compared to the amount of potassium-40 in the crystal, both of which are kind of fairly rare isotopes. So this requires two steps. One, to find out how much potassium-40 is within the crystal, and the second is how much argon-40 is within the crystal. Now, one of the beautiful things about potassium-argon dating is that the initial amount of argon-40 in the crystal can be assumed to be 0, since it's a noble gas and it was not present when the crystal was liquid and it cooled into a solid. And that the only argon-40 found within the crystal would be formed by radiogenic decay of potassium-40. One of the problems with potassium-argon dating is that you have to do two different lab methods to measure the amount of potassium-40 and the amount of argon-40 in a single crystal and not destroy it completely in the process of running those two separate tests. So ideally, what we want to do is be able to sample the exact spot on a crystal for both measurements with a single analysis. And while potassium-argon dating came about in the 1950s, it's become less common compared to another method, which is easier and more precise and only requires a single test. Argon-argon dating. So this is argon-40 to argon-39 dating. And this method uses the potassium-argon dating technique, but it makes it possible to do a single lab analysis on a single point on a crystal grain, making it much more precise than the older potassium-argon dating method. So the way it works is that a crystal containing potassium is isolated and studied under a microscope, making sure that it doesn't have any cracks or fractures in any way. So a really nice, pure, beautiful crystal. The selected crystal is subjected to neutron irradiation, which converts any of the potassium-39 isotopes to argon-39 isotopes, a gas that will be trapped within the crystal lattice structure. This is kind of the similar process that the sun does to nitrogen-14 to change it to carbon-14. So these argon-39 isotopes then join the radiogenic argon-40 isotopes in the crystal as trapped gases. So we just have to now measure the amount of argon-39 and the amount of argon-40. The argon-39 number will determine how much potassium was in the crystal. After being subjected to neutron irradiation, the sample crystal will then be zapped with a laser. And that laser is going to break through that crystal lattice structure and release both types of argon gas trapped within the crystal. This gas is sucked up with a little vacuum into a mass spectrometer to measure atomic masses of 40 and 39. Note that argon-39 is radioactive and it decays with a half-life of 269 days. So any argon-39 measured was generated by the irradiation that was done in the lab. Now this method requires really large, unfractured, really well-preserved crystals to yield good results. So the edges around fractures, around the cracks, around the edges of the crystal, any of those things might have let some of the argon-40 gas to leak out, and they'll yield too young of a date. Both potassium-argon and argon-argon dating tend to give minimum ages. So if a sample yields 30 million years with a 1 million year error, the actual age is more likely to be 31 million years than 29 million years old. And I've seen a lot of published papers where potassium-argon and argon-argon dates are much younger than the fossil or other evidence suggests, and were likely determined from fractured crystals that had some leakage of that argon-40. Studies will often show the crystal sampled and where the laser points are, and the dates calculated from each point in the crystal. The maximum age is often found near the center and far from any edge or crack within the crystal. Often this will be carried out with multiple crystals in a single rock to get a good range of dates and taking the best resulting maximum ages. Now, while potassium-argon and argon-argon are widely used, it does require nicely preserved crystals of such fragile mineral grains as biotite, which is a mica that falls apart really easy, which means that the older the rock, the less likely good crystals can be found. It also doesn't work well with transported volcanic ash layers in sedimentary rocks because the crystals quickly get damaged in the process. So because of this, geologists were really eager to use other minerals that were more rugged minerals that could last billions of years, yet preserve the chemistry of the radioactive decay. And the mineral that meets those requirements is zircon. Zircon Fission Track dating. Zircons are tough. They're really rugged minerals. They're found in many igneous and metamorphic rocks, and they're composed of zirconium silicate, which forms these small diamond-like crystals. Now, because these crystals are fairly rugged and can survive transport, They're also found in many sandstones. So these transported zircons in sedimentary rocks are called detrital zircons. With most zircon dating, you're measuring the time since the phase transition from a liquid to a solid, when the magma cooled into a solid zircon crystal. Now, Zircon Fission Track dating is much more specific. It's measuring the time since the crystal was cooled to 230 to 250 degrees Celsius, which is called the annealing temperature. Between 900 degrees Celsius and 250 degrees Celsius, the zircons are somewhat mushy, and zircon fission dating dates the cooler temperature when the crystal became hard, while the other methods date the hotter temperature when the crystal became solid. Zircons are composed of a crystal lattice of zirconium bonded to silicate. Silica and oxygen tetrahedrals. Zirconium is often replaced in the crystal lattice with atoms of similar size and bonding properties, including some of the rare earth elements. But what we're interested in is that zircon crystals contain trace amounts of uranium and thorium. Uranium and thorium are two of the largest naturally occurring atoms on the periodic table, so both of which are radioactive and decay with very long half-lives. These atoms of uranium and thorium, they act like mini bombs inside the crystal. And when one of these high atomic mass atoms decay, it sets off a really long chain reaction of ever decaying atoms, the fission of which causes damage to the internal crystal structure of the zircons. So the older the zircon crystal is, the more damage it will exhibit. Now, fission track dating was developed as an independent test of potassium-argon and argon-argon dating, as it does not require expensive mass spectrometer, but simply looking at the crystal under a powerful microscope and measuring the damage caused by the radioactivity and the radioactive decay of uranium and thorium. So fission track dating is also used to determine the thermal history of a rock as it rose up through the lithosphere and the length of time it took to cool to 250 degrees Celsius. We're at number five, uranium-lead dating of zircons. Uranium-lead dating is a very common way to date rocks and rocks containing fossils. And this method has actually kind of become nearly the standard method, as new technology has made this method much easier and simpler to obtain. So in the 1950s and 1960s, geologists were eager to figure out a way to use the uranium and lead inside zircons to get specific dates. More precise than estimates just based on fission track dating, which was, kind of somewhat subjective. Now, the problem was that all of these radioactive tiny bombs exploding in these crystals was causing damage to them over the millions of years. And this was also causing the loss of the daughter product that would escape during those decay events. So the decay of the two most common isotopes of uranium is this complex chain of events during which the noble gas of radon is actually produced as one of those steps. And so if there's any cracks or fractures in the crystal, as this is kind of exploding inside the crystal lattice, then this radon gas is just going to escape from the crystal. And as a result, the ratio would yield too young of a date. If the radon gas is still held within the crystal, it would decay back into a solid, eventually as lead. Now, lead is not found initially within zircon crystals, and radiogenic lead would only be found within zircons from the decay of uranium isotopes. And this is what allows radiometric dating using this technique. In the 1940s and 1950s, there was a young scientist named Claire Cameron Patterson, and he was trying to determine the age of the Earth by dating zircons and meteorites. And rather than look at zircons, he started looking at meteorites, which contain stable lead-204. And he used a type of uranium-lead dating that we simply call lead-lead dating. Now, Claire Patterson used what's called an isochrone, which graphically compares the ratios of lead produced by the decay of uranium and thorium, so that's lead-206 and lead-207, with stable lead, which is lead-204, which is a stable isotope, and it's not produced by the decay of radioactive uranium and thorium. So by plotting these ratios on a graph, the resulting slope would indicate the age of the sample. And this line is called an isochron, meaning the same age. Now, using lead isotopes recovered from the Canyon Diablo meteorite, Patterson actually calculated the Earth was between 4.5 and 4.6 billion years ago, and he did that in a paper that came out in January of 1956. So to acquire these ratios of lead, Claire Patterson developed the very first chemical clean room, because as he was trying to measure these different isotopes of lead, he quickly discovered abundant lead contamination in the environment around him. And this was eventually traced to the widespread use of lead in gasoline, in paints, in water pipes, all sorts of things in the 1940s and 1950s. Patterson actually dedicated much of his later life fighting various corporate lobbying groups and politicians to help enact laws prohibiting the use of lead in household products such as fuel and paints. But the year 1956 was also the year that we have the solution to the uranium-lead problem was actually solved and published on, the solution. And that was done by a scientist named George Withrill, who published a solution to the problem. And it's something called the Concordia diagram, or sometimes called the Withrill diagram, which allows the direct dating of zircons. So the way it works is that we have two types of uranium isotopes in these zircons. We have uranium-238, which is the most common, which decays to to lead-206. So uranium-238 decays to lead-206. And we have another one, uranium-235, which is the next most common isotope of uranium, and that one decays to lead-207. And those two have different half-lives, so they take a different amount of time to decay. So what you could do is you can measure these two ratios in a series of zircon crystals and compare the ratios graphically. And by doing that, you could calculate the true ratio of the zircons as if they had not lost any daughter products. So using this set of ratios, you can then determine where the two ratios would cross with a given age, and hence where they would be in accordance with each other. And it was basically this brilliant solution to this problem of daughter products kind of escaping out of zircon crystals that led to our widespread use of this technique today. Now, today, geologists can actually analyze particular points or spots on individual zircon crystals, and hence select the best spot on a crystal that has the minimum amount of leakage of daughter products. And then using the Concordia diagram allows a correction to these resulting ratios, so you can get very precise dates. Hence, uranium-lead dating requires you to determine two ratios. You have to find out the uranium-238 to lead-206, and you have to find the uranium-235 to lead-207 ratios. Now, uranium-238 to lead-206 has a half-life of 4.46 billion years. It's really long. Uranium-235 to lead-207 has a half-life of 704 million years. So both of these make them really good for million-year and billion-year scales of time. Now, to do uranium-lead dating on zircons, rock samples are ground and zircons are extracted using heavy liquid separation. And these zircons are then analyzed under a microscope. Now, zircons found in sedimentary rocks will yield the age when the zircon initially formed from magma, not when it was redeposited in a sedimentary layer or bed. So zircons found in sedimentary rocks are called detrital zircons, and they will yield maximum ages. For example, a detrital zircon that's 80 million years old could be found in sedimentary rock deposited 50 million years ago. And the 30 million year difference in time is when the zircon was exhumed and it eroded from igneous rocks and then transported down the hills into in rivers and lakes and stuff and transported into the sedimentary rock. A 50 million year old zircon will not be found in a sedimentary rock that is in fact 80 million years old. So detrital zircons will tell you only that the rock is younger than the zircon age. So fresh zircons deposited or forming within igneous rock or volcanic ash layers that contain fresh zircons, they can yield very reliable dates, particularly when the time between crystallization and deposition is minimized. So the first step of uranium-lead dating is finding and isolating the zircon crystals from rock, usually by grinding the rock up and using heavy liquid to separate out the zircon crystals. And then the zircons are then studied intensely, scrutinized under a microscope, basically to try to determine how fresh they are. If zircons are found in sedimentary rocks, they're likely going to be detrital, and you're going to observe a lot of damage to the crystals. And that damage will tell you how fresh and how young they are likely, and whether they will yield good dates or not. Now, detrital zircons are often dated in a lot of studies to determine the source of sedimentary grains by sedimentary geologists. So a lot of sedimentary geologists will look at detrital zircon distributions, and they'll note like, oh, there's a lot of zircons that are 1 billion years old. They must be eroding out of these mountains that have billion-year-old rocks. And so they do those types of analysis. They can sometimes not be very, very revealing of the actual age of the sedimentary rocks or the fossils that are contained in the sedimentary rocks. So once you've actually found a zircon, once you selected your zircon that you're interested in dating, the next step is you want to analyze them using laser ablation inductively coupled plasma mass spectrometry, which is a mouthful. It's abbreviated ALA for laser ablation, ICP, inductively coupled plasma, and MS, which is mass spectrometry. So LAICPMS, which then zaps the crystals with a little laser. And this ablated material is then sucked up and analyzed in the mass spectrometer under extremely hot temperatures, and a plasma is created which passes the atoms along a tube at high speed, measuring atomic mass of the resulting atoms, which are basically scattered along the length of the plasma tube based on their atomic mass. Now, LAICPMS measures larger atomic mass atoms. It works really good for a lot of the metals and great for lead and uranium. So LAICPMS doesn't require any real lab preparation because you're dealing with the really high atomic mass elements, which are not going to be found in the air and things like that. So you can actually analyze a lot of zircons. So a lot of studies will have really large sample sizes for the distribution of zircons, and this allows you to get very precise dates and a really good range of data. Zircon uranium dating is also the most common type of dating seen today in the geological literature, kind of exceeding even the widely used argon dating techniques. It's also one of the more affordable methods of dating, requiring less lab preparation of samples. So in part 2, I will post next week, I will explore the next 5 most common methods of dating rocks and fossils. So stay tuned and subscribe to my channel if you want to find out more. I apologize, I had some technical issues today, and so I'm filming in my office today. But I want to thank my supporters on Patreon this week: Brian Clever, Pablo Lozato Figuez, Arcodis 1811, Justin Bovey, and Fred Olney. Thank you guys. If you want to learn more about supporting this channel and in the process get access to some of the behind the scenes news items and just in general support my YouTube channel, check out the link below.